Okay, so our discussions here with momentum and are really directly pulled from Newton's second and third laws. And this video is going to focus on the connection to Newton's second law, and the next video will focus on the connection to Newton's third law. Okay, so in a previous video, we mentioned that according to Newton's second law, the net force acting on an object or a system of objects, that's the key for momentum, is it's for a system, is equal to mass times acceleration. Okay, well, if acceleration is equal to dv dt, then we get F net equal to m dv dt, or d mv dt, or since mv is momentum, dp dt. So F net equals dp dt. So F net, so the net force acting on an object, force essentially, or the net force is essentially the rate of change of momentum. Okay, and this is important. Okay, and we're gonna work this around a little bit. We can multiply the dt over, and so we get that dp is equal to F net dt. Okay, and so if we integrate this, we can integrate this from initial momentum to final momentum, and this from 0 to t. Okay, then what we find is that the change in momentum is equal to the integral, or we could just do t1 to t2, of F net dt. Okay, and so the change in momentum is equal to the integral of force with respect to time. So this is really important for us to understand, and we call this quantity work. Okay, so not work, I'm sorry. We call it impulse. Okay, and the symbol for impulse, so it's impulse. The symbol is the letter J. So J is equal to the integral of F dt. All right, so when we are analyzing situations where a force is affecting a system over time, your clue is to think of impulse and momentum. Just like in previous chapters, when you have a force that's interacting with a system over some distance, then we say that's work. Okay, and so these are basically two approaches for analyzing a system. Sometimes we could use either way. Sometimes one way makes more sense than the other. Okay, but these are two alternative methods for analyzing a situation. And so we're starting to get to the point where you actually can choose. So there's some situations that you can analyze both ways, some where impulse will make more sense, as I said. But the clue is that for impulse, that's going to help you relate a force and a time, whereas work relates a force with a displacement. Okay, so we'll focus here though on impulse, force with respect to time, and see kind of what the consequences of this approach are, or what it means really for us. Here we have a question where it says a 50 Newton force acts on a 2 kilogram crate that starts from rest, and then how fast is the crate moving 4 seconds later? So we have a crate experiencing a force of 50 newtons. Okay, has a mass of 2 kilograms, and it's going to be pushed for 4 seconds. So we have a couple ways that we can do this. Now, we can use kinematics here. We can divide 50 by 2 to get acceleration. We can use acceleration to find velocity. Okay, but the other approach that we have here is using impulse. Okay, and so what happens is that we can use this concept of impulse as the change in momentum. And so we know that the way that we do this is that impulse, or change in momentum, is equal to the integral of F dt. Now what this means is a couple things. First, we can say, all right, it's a constant force, so we're going to iterate from 0 to 4 seconds, the force of 50 newtons with respect to time dt. Okay, and so that's going to give us 50t, and then we'll evaluate from 0 to 4 seconds, and so that gives us 200. This would be Newton seconds, okay, is our change in momentum. The second option is this. Remember, the integral is the same thing as finding the area beneath the curve or the graph. So if we have a constant force here of 50 newtons that lasts for 4 seconds, if we find the area of this graph, that gives us 200 Newton seconds. Okay, the third thing that we can do is, if we know that the force is constant, if it's a variable force, we have to use this. If the force is constant, we can use this. We can say just delta P equals F times T, like here for a constant force. And so we're going to say 50 times 4 seconds equal to 200 Newton seconds. Okay, so now we'll say, okay, so we have some initial momentum, and we add to that our impulse, our change in momentum is going to give us our final momentum. Okay, and so in this case, our change is 200 Newton seconds. All right, well, the units for momentum are kilogram meters per second, and that doesn't look like Newton seconds. So we have to kind of show that those are the same real quick. So remember that a Newton is a kilogram meter per second squared. So if we multiply that by a second, one of those is going to go away and get kilogram meters per second. Okay, so we then have an initial momentum mv of 0 because we have velocity of 0. So 0 plus 200 kilogram meters per second will be equal to our final momentum, our mass of 2 kilograms, times our velocity v. Okay, so we can solve this, and we find the velocity is going to be 100 meters per second. Okay, and there you go. We used impulse to find change in momentum, and to then find the velocity. So here we have a scenario where we have a graph showing force versus time, and we have a variable force that's going to peak at 20,000 newtons, and the total interaction is going to take 2/1000ths of a second. Okay, and so it's going to happen really fast. And so what I'm trying to do here is simulate what the impulse might look like, or the force time graph might look like for a baseball bat hitting a baseball. So if we have a 0.15 kilogram object, the baseball, going with a velocity of negative 40 meters per second, experiencing a force that maxes out at a positive 20,000 newtons, how fast is the baseball going afterwards? Okay, and so I'm going to ask you to solve for this, and the hint that I'm going to give you is, I'm going to give you 2 hints. Remember that impulse can be found by finding the area under the force time curve, and remember that the area of a triangle is 1/2 times base times height. So we have a base and a height, okay, and you can use that to solve for your impulse and find your final velocity. Okay, so when you set it up, m times v plus delta p, so our change in momentum will be area here 1/2 times our height, 20,000 times 0.002 seconds, will be equal to our final momentum. We can simplify here, solve here, and simplify. We get negative momentum to start with. We have a positive change in momentum, and so we'll combine those to get 14 kilogram meters per second equals 0.15 kilograms times v, and we get that v is equal to 93 meters per second. This seems a little bit unrealistic to me. I'm guessing probably the time was too long or the force was too much, because 93 meters per second would be like 200 miles per hour, more than 200 miles per hour, which I don't think, yeah, just over 200 miles per hour. I don't think that baseballs travel that fast, so maybe they do. I don't know. Anyway, that's kind of how we would use it there. And then I'm also going to talk real quick about just kind of the concept of impulse too. So I want to talk a little bit about impulse conceptually, think about what's going on, and there's kind of there's something that's going on underneath here that's important to think about. So, and we're going to use the example of an egg. So if you were to take an egg and you were to drop it, you could drop it on a slab of concrete or like a pillow, kind of try sort of a pillow. It's not a pillow, but whatever. You get the idea. So anyway, if you drop the egg on the concrete, it's going to break and splatter everywhere. If you drop it on the pillow, it'll be okay. And so, I mean, instinctively we know, well, of course it's going to break on the concrete because the concrete is hard. And of course it's okay on the pillow because the pillow is soft. Okay? But technically, you could have like a concrete like chunk that you catch the egg with and it would survive. And technically, you could actually break an egg with the pillow if you were moving the pillow fast enough. Okay, if you like moved it up to catch it or something. Okay, and so the key here is this idea of impulse. So in both cases, the change in momentum of the egg is the same because they're both being brought to a stop. Okay, and remember, change in momentum is impulse. Well, in one case, you experience a large force over a short time. In the other case, you experience a small force over a longer time. So the key here is the amount of time the collision takes. The longer the collision, the less force we're going to experience. The shorter the collision, the more force. And force is the measurement of pain experienced by the egg. Okay? And so if we were trying to drop the egg and protect it, the key would be to minimize that force. And if you're trying to break the egg, you will want to get that force to be as strong as possible. Okay? And so the key here, long collision means small force. So long collision means small force, whereas a short collision means really strong force. Okay, and this cartoon is kind of an example. Okay, so someone getting punched in the face, either way, that fist is coming to a stop on their face. But if it takes a long time to do so, that means you're experiencing a small force, and so you have little pain, versus if it is a large force and happens really quickly, which is a lot of pain. Okay, and so that's an important concept here with impulse. So we're going to do one more question and we'll wrap up the video. Okay, so the last question here is a 2.5 kilogram stone is released from rest and falls towards the earth. After 4 seconds, the magnitude of its momentum is blank. So go ahead and choose the option to the right. And please let me know if you have any questions after watching this video.